Welcome to qnawire.
So the first part of this question asks us to work out the separation distance R0 at which the energy of a molecule is minimum given this Lennard-Jones potential equation here. So when the potential energy of the molecule is minimum, we know that du by dr will be equal to 0. While differentiating, we will decrease the power by 1 and we will multiply the original power up. So taking that to be ar to the minus 12, for example, we end up with minus 12a over r to the 13 plus 6b over r to the 7. And now the equilibrium position R0, we will just sub that into our value for R, and we will set that equation equal to 0. And all we need to do now is rearrange. So all I've done is taken the 12a to one side here, and the 6b over the R0 to the 7 term on the other side. And all we need to do now is solve for R0. So taking the R0 terms to its own side and the constant values to the other, we end up with R0 to the 6, because R0 to the 13 divided by R0 to the 7 is R0 to the 6, is equal to 2a over b. And as such, our equilibrium position R0 will be equal to 2a over b to the power of 1 over 6. Now you might just think to sub in the constant values here. However, on most calculators, typing in a value as small as 10 to the minus 120 will cause your calculator to provide an error. So what we're going to do is just collect our powers of 10 terms just to one side of the fraction. So that will end up being R0 is equal to 2 times, and then our a value, which is 0.124. However, we'll take the 10 to the minus 60 power to the top, so that will end up adding to the power because we're dividing by a negative power. So that'll be times 10 to the minus 60, which is manageable for pretty much all calculators. And that will be all over our b factor, which is 1.488. All to the power of a sixth. And this comes out as 74.2 picometers. So part B of the question asks us to work out the energy E required to break up this molecule. So we already have our equilibrium position that we worked out in the last part. So all we need to do is substitute that into our equation for the Lennard-Jones potential. So substituting in our constants as well as our value for R0, we end up with U of R0 is equal to all of this. Now the problem is if we type all this into a calculator, we will probably end up with errors because of the such small numbers that we're using here. So we need to collect our powers of 10 again. So this will be equal to 0.124 times 10 to the minus 120 over, and now we're going to split this bracket up using indice rules. So that's 74.2 to the power of 12 times 10, and now minus 12 times 12 is minus 144, minus our value for b over 74.2 to the 6 times 10 to the, well, minus 12 times 6 is minus 72. And taking our powers of 10 on the denominator up to the numerator, we end up with this expression, which is much more manageable for a calculator to determine. And putting all of that in comes out as minus 4.46 electron volts. Now, because it's a separation energy, we actually don't need the minus sign there. It's going to be a positive value. So the final answer will be 4.46 electron volts.